Hello and welcome to the fourth and final day of our Policy and Practice Forum. My name is John Grassel and I am your moderator. This no-cost virtual Firearm and Toolmarks Policy and Practice Forum is brought to you by the National Institute of Justice and the Forensic Technology Center of Excellence. Over the past 3 days, we have heard from forensic firearm and toolmark analysis stakeholders in research, emerging technologies, and intelligence-related discussions. Today's topic is legal aspects and will be followed by a special panel focused on the next steps within the field. Our keynote presenter for today is Erich Smith, who is a physical scientist, forensic examiner, and technical leader for the FBI laboratory. He will discuss the accuracy, repeatability, and reproducibility of firearms toolmarks comparisons. Erich Smith is also a member of the Association of Firearm and Toolmark Examiners and the European Network of Forensic Science Institutes. Prior to the FBI laboratory, Mr. Smith worked at the Virginia Division of Forensic Science and has been a qualified examiner with the FBI laboratory since 2002. He was a member of the OSAC subcommittee for physics and patent interpretation and has been at the forefront working with and evaluating novel 3D technologies for the firearms toolmarks disciplines since 2013. Welcome, Erich.
I want to thank everybody joining the meeting today. My name is Erich Smith. I'm a firearms and toolmark examiner at the FBI laboratory, and I'm going to walk you through our recent black box study titled The Accuracy, Repeatability, and Reproducibility of Firearms and Toolmark Comparisons. I'd like to first call out some individuals that were very instrumental in bringing this product and research together. With the members of the FBI team, it was myself, research scientist Keith Monson, and Jennifer Stevenson, a technician in our laboratory at the time. These are the three individuals that worked primarily on this project. And then I cannot offer enough thanks to the researchers at Ames Laboratory, specifically Scott Chumbley, Stan Bajic, Max Morris, and Daniel Zamzow. These are the individuals that had the large task of keeping track of everything and producing the product in the end. As with all presentations, I have to give a disclaimer. The names of commercial manufacturers are provided for identification purposes only, and inclusion does not imply endorsement of the manufacturer or its products or services by the FBI. Any reproduction or other uses of these presentation materials without the express written consent of the FBI is prohibited. The views are those of the authors and do not essentially reflect the official policy or position of the FBI or the US Code. For our presentation today, I really kind of want to give you an overview how what our decision was to move forward with a black box study. I'm actually going to peel back the hood a little bit and let you look at one of the tests, how we actually came to put all the pieces together, and then how we handed it off to Ames Laboratory and their crunching of the data basically and keeping track of the data in the end. So the genesis of this black box study was primarily admissibility challenges from Daubert from 1993. We also wanted to address some of the NAS report criticisms for the discipline of firearms and toolmark identification. We also saw some effectiveness of the decision analysis study from the latent print examiners, which was conducted by the FBI in 2011. And then I also wanted to point out that we wanted to address some of the shortcomings of previous studies, some not being double-blind, closed sets, which we'll talk about in a minute, and limited to striated marks, meaning most of the time when you look at validation studies for black box, for firearms and toolmark identification, they deal primarily with bullets or cartridge cases specifically. Here we're looking at both. So the design of the decision analysis study pretty much took place around in 2012. So we've been working on it for a long time, thinking of different parts that we wanted to tackle in the study. We had to raise internal funding. This is a large project involving numerous samples, and we had to secure the funds. We contracted with an IRB, and then we executed the study. I think it's probably a good time to look back at the studies that exist within the Firearms and Toolmark discipline. These are three categories that typically are mentioned when looking at work that's been done to support the validity of the science. So I'm just going to briefly go through the three types of set designs, and then just point out the advantages of the three. Early on, most of the test designs were within set. So within set basically is you have a group of cartridge cases. Examiner receives, let's say, 10 cartridge cases and is asked to intercompare them and try to connect if there are any identifications or eliminations within that set. The other set comparison is a set-to-set comparison. In this situation, you have a series of cartridge cases that may be questioned that are now being compared to known sets. So here are a series of guns, here's a series of cartridge cases or bullets, intercompare them and try to reach a conclusion. In a partially open set, there may be more questioned cartridge cases than known guns or vice versa. And then finally, the independent comparison or the one-to-one comparison set, which our black box is, to include the Baldwin study, which has typically been called out as being a very good study design initially. That's where an examiner gets a question item, whether it's a bullet or cartridge case, and then they're given two knowns or a known, and they're asked to make the decision, was this bullet or cartridge case fired from that gun? So this is typically the type of test design that we see most often now. The thing I would like to point out is with the within set and the set-to-set comparison, those are more typical of what an examiner actually experiences in casework. So when you're looking at those test designs, that is typically how an examiner is receiving evidence and asked to reach source conclusions in that type of test design. The disadvantage of that is that sometimes it's not easily known what the error rate may or may not be. Examiners perform very well with those types of tests because there's a lot of information and they can reach the right source conclusions. Where you have the one-to-one set comparison, you're just focused on that one decision and it's easily calculated as far as the error rate in that type of test design. Right, so the study goals. We basically wanted to validate the reliability of forensic firearms identification. There's plenty of data out there that shows that we can do a comparison, reach the proper source conclusion, but we were looking at some of the recommendations of the 2009 NAS report and the PCAST to help further the science. We wanted to characterize the overall error rate, and then we were also going to branch out into some other areas where they hadn't been looked at before. That was the repeatability of a decision, meaning if I was the examiner, could I repeat the same conclusion if I saw the same samples at a later date? And reproducibility. What is the decision by another examiner based on what I've looked at? Do we reach the same conclusion? The test design was built as double blind. So that meant it required a third party to handle the test distribution and data collection, and that was done by Ames Laboratory. One thing that we did, which we had noticed in other test designs, is that unlike before, the tests weren't randomized, meaning that I could receive a test and a coworker could receive the same test, so the answers might be the same between the two tests. So in our test design, everything's randomized. So if I received a test, my answers or the number of ground truths in that test might be different versus somebody else taking the test. So each one was independent. We utilized both cartridge cases and bullets for our tests. And this is probably the most difficult thing that I had to do in the test design, is trying to bias it towards difficult and hard samples. And one of the ways that you can do that is you provide a test that has a considerable number of known non-matches, meaning there are a lot of pairs that don't match. And that's trying to tease out the possible error rate by making it more difficult. And so that was one of the things that we had to consider. So in our test design, the total number of true matches of packets was 33, a third. We also included test samples that had subclass. And for those of you who aren't familiar with that, those are situations where in the manufacturing, a mark or a few series of marks might translate between more than one workpiece. So when you're looking at consecutively manufactured barrels or breech faces, barrel A versus barrel B, there might be some coincidental mark that translates between both of those barrels, those two barrels. So that's one of the things that we wanted to evaluate. And did that have an effect on the decisions of the examiners? And the other advantage that we had with our test is that we got to look at the persistence, meaning that as we were test firing, we were tracking time-wise the shot sequence. So we could see what was the effect of wear on the decision of the examiners throughout the test. So for our test design, one of the things that we did is we had a pre-distribution test. We assembled different samples using different guns, different types of ammunition, sent them out to examiners and asked them, we actually put together a review sheet so they could give us feedback on what they felt was difficult, what was easy, some suggestions that they had on the test itself. So we did all that ahead of time to tease out the things that we wanted to use in our test design. Part of it, we wanted the majority of the test participants to be AFTE members. That is the Association of Firearms and Toolmarks Examiners, and also coming from an ASCLD or ANAB accredited laboratory. We also wanted the examiners to use the AFTE range of conclusions. So for the AFTE theory of identification, there are 5 levels, meaning there's an identification, and then inconclusive, but with the inconclusive, there are 3 categories. Category A, meaning that there is some similarity, but insufficient to make an identification. And category C, meaning that there's dissimilarity, but not significant enough that you could eliminate on. And then we also had unsuitable. One of the things that you should also consider, examiners were asked to do this solely. So they are extracted from the quality assurance system. So they don't have the benefit of a verification when they're making their decision. It's solely their decision based on their experience and training in the application of the AFTE theory. Results were anonymous. We also sent out a questionnaire. We wanted to know a lot of information about the instrument that they used, the methodology they used, such as CMS, consecutive matches STRIA. We wanted their feedback on the complexity that they felt there was with the comparison and the amount of time it took them to come to a conclusion. So all this data was being collected on every one of the comparisons. The FBI, we test fired all these firearms and all the ammunition. We test fired them in groups of 50. So basically a box of ammunition had 50 cartridges. Those are fired each, they were cataloged initially and then fired in groups of 50. At the end, they were sent to Ames for the test packet assembly. For our design, we selected 3 pistols, and you can see them located at the bottom of the screen. It was the Beretta M9A3. We used 27 of those. The Ruger SR9, we used 11 of those, specifically the barrels. And then we used the Jimenez JA9. We used 11 of those. And just for your knowledge, looking at the quality of the firearms, the Beretta and the Ruger are a higher quality. They're a more expensive firearm. The Jimenez is a lower quality, lower cost point firearm. And so the quality and the construction of that is less than that of the Beretta and Ruger. So let's talk about the actual manufacturing process. So for the barrels and slides, machined by a single final tool, either selected at consecutive intervals over the life of the tool, meaning that we would actually watch 3 being made initially when the tool was initially started in production and then moved further down the line of production, grabbed 3 more that were consecutively made, and further down, grabbed 3 more until the tool was removed from service. So we have the history of that whole tool in its production, as well as consecutive elements along the way. We had a break-in period of approximately 100 rounds for the firearms or barrels that were selected. We also pulled some additional barrels and slides from our reference firearm collection at the FBI laboratory to nestle some ground truth known non-matches within the test. In total, each Ruger was test fired 850 times. That resulted in 9,350 bullets. And each Beretta was test fired 700 times, resulting in 18,900 Beretta bullets. And each Jimenez was fired 880 times, resulting in 9,350 bullets and cartridge cases. One thing to understand about the manufacturing for the barrels, the Ruger and Beretta barrels are either double broach or triple broach. And for manufacturing, for a firearms examiner, these are types of manufacturing processes that we understand can create subclass characteristics potentially. So this manufacturing technique we know can produce subclass, and we were trying to put that into the test design to try to create false positives, creating a more difficult test. So one of the things that I mentioned early on is that we wanted to talk about tool wear and persistence. So in the pictures here, I have a broach tool on the left. That is the actual tool that will cut the rifling in the barrel on the right. So you're looking at the inside of a barrel, specifically the landing, 2 grooves. As we were able to track the sequence of test firing, we are evaluating the reproduction of the tool marks over time. Is there a degradation, a reduction in the quality of those tool marks being able to reproduce as the barrel is wearing out? And what type of impact would that have on an examiner's decision? We did go through a process of cleaning the firearms. As you can see, after 250 test fires, we would clean just a general cleaning, not a complete breakdown of the firearm, but running a patch through the barrel to clean it out and wiping off the breech face. This was a pretty challenging task for myself and Jenny. We wanted to make sure, I guess, to be quite honest, my biggest fear is that we'd send things off to Ames and there was some cataloging issues and we wouldn't be able to identify where an error in cataloging went. So we came up with a plan ahead of time to create bins, as you can see on the left. Each bin contains one of the particular Berettas that we were going to test fire. And so when a particular Beretta was going to go to the water tank to be test fired, you would pick up the bin and the bin would have boxes of ammunition in it that were already cataloged. And that's how we kept track. So there was no commingling of firearms and ammunition. So there would be no potential for what we call cross-contamination or loss of tracking. Another thing that we did prior to test firing, and this is the picture on the right, typically in our research, we cast both the breech face and the barrel as received. So this was the process. Each one of these slides and barrels was cast. So we have a permanent record of what that tool marked surface looked like before we began. One of the most difficult things we had to make a decision on was ammunition type. And ammunition plays an important role in the tool mark reproduction. For firearms examiners, we know this straight away that some ammunition marks well compared to others. And the reason being is one of the effects called obturation. That's a fancy word talking about how well the cartridge case is going to expand and seal off the chamber, as well as the bullet engaging with the barrel. The less that it obturates, the less contact it makes, the less it's going to transfer the individual characteristics to either the cartridge case or the bullet. So I can go in, I can test fire 2 cartridges. I've test fired it. I know it came from that gun, but then when I go to do the comparison, there's a lack of reproduction between the two. One may have had a plethora of tool marks, individual characteristics, and the second one may not. And then you really don't have enough information to make a decision, even though I know they came from the same gun. So that's one of the limitations. And I think that's missed quite often by people that aren't subject matter experts. So for our study, we selected Wolf ammunition. It's a Russian made. And actually, I've talked earlier about how we tracked all the ammunition in lots and in firing sequence. You can see on the box there, it says Ruger CB6, so that's consecutive barrel number 6. And this is test fire 411 and 400 to 460 for that consecutive barrel number 6. So that's how we track them. And you can see the difficulty for these types of ammunition components is both the bullet, it's steel with a copper plating, so it doesn't tend to translate the individual characteristics readily, as well as the cartridge case is steel. So this was the ammunition that we ended up selecting in the end. So the test is designed to be difficult for the number of choices. The firearms selected are difficult as well as the ammunition. And the picture at the bottom right, that is the water tank room that all these test fires were captured in. Right, so this is where we're going to peel back and actually take a look at the test samples. So this is the Beretta. The subject matter expert, I kind of understand when I see a cartridge case that it may have been fired from this particular type of firearm based on the characteristics that are left behind. But if you look at the picture on the left, we are actually looking at the breech face of the firearm that's depicted at the top. So you see these arcing lines that are running across the breech face. This is a milling process to cut this surface. It looks very similar amongst all the samples that we have. So there's going to be a mill that came through at a certain rate and speed, and they all have these arcing lines, very similar to one another. Dead center is the firing pin. So that's another feature that we can use for identification. And then on the left-hand side, that's the extractor. That's the device that actually pulls the cartridge case out of the chamber. The picture on the right, that is the same breech face after all the test fire. So what you see now is there's a wearing of those arcing lines. They're not as pronounced. And now we also see some material that's being left behind. It kind of sparkles a little bit, but that's actually coming from the cartridge cases. They're actually leaving deposits of metal behind. And then there's sooting. The carbon buildup from the burning of the powder is also left behind as well. So all those features and variabilities are building on top of the individual characteristics that are present in the manufacturing. The other one that we selected for cartridge cases was the M&S. So this is our lower price point firearm, depicted on the left. And we'll talk about the picture on the bottom left as well. So this is the breech face again. The firing pin is the little circle in the center. And then at 6 o'clock, that little rectangular feature, that is the extractor. And then the red device, that is a load indicator. And then at 3 o'clock, there's a protrusion, kind of L-shaped feature. You can't see it completely. That's the ejector for this firearm. So what we are concerned about is how this surface is actually manufactured. Different than the Beretta. The Beretta used a milling, and this one uses a turning. So if we look at the comparison on the right, these are two test fires from two consecutively made M&S. And you can see there's this gross circular lines. These are concentric circles. That's how we describe them. And then also in the firing pin, you can see they're concentric circles as well. So this was a turning method to produce this. If you think about a record, one that you would play, if you remember records, it's kind of the same thing. You see these concentric circles. Concentric circles can be, they can be challenging. They can be misleading because if you're using the same turn rate to produce multiple items, you're going to have concentric circles that fall in the same plane, in the same position. So examiners are trained like, I can look at these, they may give me some understanding of orientation, but I really shouldn't use them for identification purposes. I should look at breaks, interruptions within the lines to make that the identification for individual characteristics. Not much different than if your record got a scratch on it. It's going to skip in that spot, as opposed to another record that doesn't have a scratch in it. That's the type of detail that the examiner is focused on. But it also makes it more challenging for the examiner as far as the comparison. All right, at the end, we had to come up with a way to assemble the packets because we wanted to test repeatability, meaning I looked at it one time, I see it again, but I don't realize I've seen it once, as well as reproducibility. So we elected to use a barcode for tracking all of our samples. So On the pictures at the bottom, on the left, we've got the bullets, and we have a little device that we had made to support the bullet. And then you can see the barcode. We went so far as to color code the knowns. So anything that was blue, the examiner knew was a known. So they would get 2 known test fires from the gun, and the question was in white. We wanted to make sure that just visually they wouldn't be able to mix things up, and they would always know what they were looking at. The cartridge cases, we couldn't do that. So if you look at it, it says K for known on the cartridge case, and the question has just the barcode. The real trick here is we have thousands of bullets, and how are we going to mount them to these posts? And we came up with this device in-house, this little jig that we sent off to Ames. And you can see how the post would sit at the bottom, the bullet gets dropped through, and epoxy binds the bullet to the holder device. At this point, everything, our job's done, and now we're sending it off to Ames. And Ames is taking over the project with distribution, cataloging all the information, and tabulating the data. So for Ames, they assembled the test packets. They were left to affix the bullets to the holders, and they applied the barcodes. So we shipped everything to them with the concept of how to assemble them, and then they actually took on the yeomanship work of doing all of it. Each test packet, if you were to receive one, had 15 cartridge case sets and 15 bullet sets. They handled the mailing and distribution. They tracked, in the recording, they tracked the manufacturer and the manufacturing sequence. So in later papers that are published, you'll be able to see there'll be a catalog of early, mid, and late based on the firing sequence. They did the redistribution for repeatability and reproducibility. They tabulated all the survey results and collected feedback from participants. They generated the data for the DNA, for the decision analysis, and they provided the report and participated in the publication of the results. So with this chart, I really want to kind of point out the test participants, test response. Myself, I went to an AFTI meeting in New Orleans a few years ago to announce that we were doing this study and put out a call to examiners to join up. And as in all studies, all examiners are they're committed to furthering the science. And we had a lot of people sign up in the beginning. As you can see, there were 250 people that signed up to participate, which is a good number. Actually, if you look at the x-axis, that's the number of distributions. So there were 6 total distributions of the test packets. So in the first distribution, we see we have 250 people that signed up, and then we have a large dropout. As an examiner, when I have to participate in one of these studies, it can be tough to kind of balance your casework and other responsibilities and also participate in something that takes a lot of time. And so we had a lot of people drop out in the beginning, but we still had a lot of people return scores. Over 150 people provided scores on the precision portion of the study. But you can see historically, which is true with a lot of studies, there's attrition. And so in the end, at the 6th distribution, we have around 75 people that completed the total number of 6 distributions, which is pretty good, which gave us a lot of data to work with on both the reproducibility and repeatability. All right, so let me kind of give you this is the big picture on everything that went out. So we talked about there were 6 total mailings. So in round 1, that was the accuracy. What's the false positive, false negative? That's what we were looking for. Round 2 is about the repeatability. Could I get the same answer again? And reproducibility is round 3. What does another examiner say versus my opinion? So you look at the chart, you can see how the distributions went with the number of samples. So in the end, on the right, you see the 10,020. That was the total number of comparisons using bullets. And then for cartridge cases, there was 10,110 comparisons. So a lot of information, a lot of knowledge being gathered from these different comparisons. So let's look at the overall accuracy of the results. So this is the first distribution, and we're tracking the false positive and false negative in this category. True throughout, but this is really looking at the accuracy of the results. So if you look at the chart at the top, we've got the bullet comparisons teased out. And you can see for false positives, it's 0.66%. It's very low. And we also have the uncertainty boundaries around it. So it can't be as high as 1.4% at 95% confidence interval. And then for false negative, it's 2.87%. A little bit higher, but that's to be understood because these samples are more difficult. They may provide information that might tend to be misleading and cause the examiner to make a false elimination. So the bounds for that, for its uncertainty, is around 1.89 to 4.2%. Now looking at the cartridge case comparisons, we have a lot of parentheticals there. These are the actual results from the Baldwin study, which was highlighted in the PCAST as being a good test design, where we're looking at a one-to-one open set test design. Again, examiners did very well. So for false positives, cartridge cases in the black box study of the FBI, 0.93%. Tracks very similar to the Baldwin, which was right at 1%. False negatives again, 1.87. It's higher. Again, to be expected, these samples are difficult and they may be providing information that's allowing an examiner to make an elimination erroneously. And then you can see the confidence intervals at 95% to the right. So with the cartridge case comparison, it tracks exactly, or very similar, not exactly, but similar to the Baldwin study. So one of the other things that we wanted to pull out of the data, which you see in other tests, is the sensitivity and specificity that was tracked. And so in this table here, we can just look at the top portion with the bullet comparisons. If we look at the sensitivity, these are the, talking about the identifications. You can see the calculations. So the number of recorded identifications is 1,076, and the number of true known match identifications is 1,405. So it roughly equals 76.6% for sensitivity. So this gives you a good indication of the difficulty of the test. Where they were not able to effectively come to a source conclusion, 100%, at a high percentage level. And then specificity looks at the eliminations. So again, you've got the table there for the bullets. There are 961 recorded out of the 2842 known eliminations. That's roughly around 33.8%. One thing, and actually looking at that number, one thing that you should consider is that in some laboratories, mine in particular, as well as others, we don't eliminate on a difference in individual characteristics. And that has to be, that has to be known that, as we talked about before, one of the limitations is the reproduction of the toolmark. So there may not be enough information to eliminate. And so if I just based it on, well, I don't have enough information, I'm going to eliminate, that would be a false elimination. If all the class characteristics are the same, I can't eliminate solely on a difference in individual characteristics. So it stands to reason that if other laboratories are following that same methodology, it would make the specificity lower. Right, so I wanted to kind of give you a sense of what did this cartridge case, what do they look like? What does a test look like? So I'm going to show you one of the false positives. So this was cartridge case group 680, set 3. What you're looking at here are two of the knowns that were in the test packet. So this came from the Beretta, I can tell right off the bat. And if you remember from the picture, I showed you the breech face, you can see the arcing lines, how they reproduce. So if you look at the image on the right, you can see these lines that run almost from 3 o'clock all the way over to 9 o'clock in an arcing fashion. They're more pronounced towards the bottom than they are towards the top. If you look at the cartridge case on the left, it came from the same gun, but it didn't translate the same amount of information. And so one thing that stands out is you can look at the primer, that's the brass colored feature. The diameters are different between them. So the one on the left did not come in contact completely with the breech face. So not as much information translated over. The donut shaped ring that you see, that's from the aperture. It provides little if no information. And then the firing pin impression has just a small defect, but it's predominantly smooth. So there's very limited information there. So let's take a look at what the comparison looked like. All right, so the image on the right didn't change. That's still the test fire. The image on the left is the question sample from the test packet. So was the question item fired from that gun? That's what we're asking you. Well, lo and behold, the one on the left looks like it was fired from a Beretta. I see arcing lines. There are arcing lines between the two of them. But if you look at roughly on the one on the left, between the 2 and 10 o'clock, that deep arc, it's a very pronounced arc, that's not on the one on the right. Now that may be a factor of reproduction, but it's not there. To include the gross one that runs between 4 and 8 o'clock, it's not the same diameter, although it's in the relative same position. It doesn't have the same quality as the one on the right. And then looking at the donut feature, at a roughly, let's say around 8 o'clock, there's a protrusion, an artifact, a defect on the one on the left. And the one on the right is completely round. So there's a lot of dissimilarity between the question one than there is between the known. This is a good situation where the arcing lines do provide some ambiguity. It looks like that things should fall into place, but a closer look at it, closer inspection, you can find there's not the sufficient agreement that you expect with an identification. So this is a good example of a manufacturing method that reproduces consistent arcing lines that it requires the examiner to look a little closer. So let's talk about the test as a whole for the accuracy. So the false positives were about the same as the Baldwins. Higher error rates for false negatives, and we talked about that. That's due to the difficulty of the mixture of ammunition and firearm. We also had a wider spread of firing order, which the Baldwin study did not have. So 100 versus 700 or greater. So that talks to persistence, how the toolmark survive. As with the Baldwin study, as with our study, the errors that were committed by the same, like a pool, same group of people. So there's a small subset that is creating the majority of the errors. So 139 of the 173 examiners made no errors. So 112 errors from 20,130 total comparisons. Those are pretty good. That's very good. Figure that 20,000 comparisons, there are only 112 errors. That's very good. Cartridge cases had 51 of the errors and bullets 61. So 6 examiners accounted for 33 of the 112 errors, approximately 30%, and 13 examiners accounted for 54 of the 112. Tabulating this information, Ames decided, specifically Max Morris, that this justified using an individual beta distribution rather than a single binomial distribution for calculating the information for the examiners. So at this point, we're gonna tease through the repeatability and reproducibility. So we're gonna break it down by the bullets and the cartridge cases. One of the things, this chart's, there's a lot of information on this chart, but what I'd like you to kind of focus in on is the green diagonal. So if you remember, repeatability is I make a decision, and then sometime in the future, these bullets or cartridge cases come to me again. I don't know that I've looked at them before. Do I reach the same decision? So at the top left, the 665, that's 665 times examiners were able to reach the same decision when presented the same samples again. And then you can see through the center during the inconclusive A, 28 examiners did the same decision second time around. Inconclusive B, 45 of them did the same decision. So that's how these charts work. For the portions of paired agreements for bullets, we did very well. So it's around 76%. That's for the matching set. And then for the bottom chart, the bottom of the chart, that has to do with the known non-matching set. So these are the eliminations. It's flipped. If you look at the chart on the bottom right, where you have 514 times examiners, or 514 examiners eliminated the second time they saw the set. So in this situation, the portion of paired agreements is roughly 64.7%. That's very good. And this is very good data that supports that the examiner, when looking at this thing presented again, pretty much lands on the same decision. The thing that I do want to point out on the known non-matching sets, most of the information is classified between inconclusive A and C. So the examiners understand that there's not enough information to conclude that they were fired from the same, but they're trying to figure out what's the level of disagreement between the two samples. So that's the total for repeatability for bullets. Let's take a look at the cartridge cases. So we have the same thing again. Looking at the total matching sets, the portion of paired agreements is 75.6%. Still very, very good. And now we've looked at the bottom at the known non-matching sets for cartridge cases. Look at the elimination, 718 times the examiners eliminated. And then you can still see within the inconclusive range, the examiners are trying to land on the amount of disagreement, knowing that this is not a matching set. Now let's move to reproducibility. So this is now, I've looked at it, I've made a decision, and now another examiner looks at it and looks their decision. Starts the same way. We're looking at the bullets, top left, 601 times. So 601 times the examiners, two examiners agreed to the same decision. And if you look at it, the portion of paired agreement is 67.8%. Still very high, tracking very good. Now with the known non-matching sets. This is interesting because the eliminations are 274. So if I said elimination, another examiner said elimination, 274 times. But the portion of paired agreements is 30.9%. So think about that. Why is it's lower at 30.9%? I have to really give credit to Scott Chumley for an analogy that works really well to explain this. He gave an example when we gave this presentation at the American Academy. And he used a box of crayons. He tells the story like when he was little, he had a box of 8 crayons. So he only had a few colors in there. There were other kids that had the 64 box crayons. And so they had an assortment of shades of colors. If you look at, you just keep that in your mind, but you look at the known non-matching sets. Examiners in the inconclusive range, they understand they're doing this comparison. They don't find sufficient agreement between the two samples. So it's not an identification. So now they're asked to try to express the dissimilarity that they're seeing between the two. Now think back to the boxes of crayons. I've got 8, and another child has 64. And the teacher says, pull out your green. But I only have 1 green. It's very easy for me to pull out green. But the other child has maybe 5 shades of green. And they're trying to pick which green does the teacher want to pick out. So that's where you see this expression in the inconclusive range where the examiners are trying to give you an indication of the dissimilarity. They track mostly within the inconclusive A and inconclusive C, which that stands to reason that the portion of paired agreements is lower. And it's a non-matching set. Same thing with cartridge cases. So very good paired portion agreement with matching sets. So 582 times the examiners reached identification. And then we see the same phenomenon that I just explained with the no non-matching sets. Examiners 530 times that they didn't match, but then they're grappling with inconclusive as well. So that's why the portion of paired agreements is lower for the no non-matching sets. One thing that should be pointed out is there's the limitation that we talked about with the reproduction of the toolmark. If there's a reduction in the expression, if you remember back to the cartridge cases where I compared the two knowns, they were both fired from the same gun, but one didn't reproduce the same amount of information. Now you have to try to express that. That's what you're seeing with this data, is that the examiner is trying to grapple with what is the dissimilarity if I don't have enough information. One thing that we can look at is repeating errors. So repeating errors, did I say false positive and then later on I said false negative? Or did I say false? Did I get the correct answer and then another examiner looked at it and they said false negative? All these different areas with different errors that might be expressing themselves. So we didn't see much of that. So with the false positives, we did have a bullet set that did have more than one repeating error. And then with cartridge cases, we didn't. And then with false negatives, we did see Bullet sets, we had 4 of them, and with cartridge case sets, we had 2 of them. And then we had a single sample that created an error in all 3 rounds. You have to think about what implication does that have? It really goes to the laboratory's quality system. If you think about in a laboratory, when I make an identification, I come to a source conclusion of identification. It doesn't go out of the lab until another person looks at that. If I were to be incorrect, and let's say in this situation, I'm making a false positive in my train of thought, and then another examiner comes along and asks to look at it independently, the data suggests it's unlikely that that person would make the same mistake. That's what the data is supporting. So as far as casework and how the quality system works in the laboratory, this helps to support that. It's very unlikely that a second examiner, when they look at it independently, that they're going to make the same mistake. Okay, so more data that, to me, this was unexpected, but it's nice to see, and it helps support basically our business model and our quality. So overall, just to kind of close out, we had high accuracy. False positive rates were the same as Baldwin, and the false negative rates were somewhat higher. High repeatability, so the examiner pretty much lands on the same decision over and over again. So overall portion of paired agreements exceeds 75% for known matches and 60% for known non-matches. So that's better than chance. High reproducibility. Portion of paired agreements exceeds 63 for known non-matches, and portions considerably lower for non-matches. This is a result of multiple ways of characterizing the crayon. So in the future, we've got several publications that we're working on. These are some of them listed here. The one that we're talking about here, the accuracy, this one is currently under peer review and should be published soon. There's probably more than just these 4, but right now we definitely are following with these 4 as far as data. Closing out, I'd like to thank a couple individuals that have had a lot of influence and a lot of support to put this product together, collect the data. Gene Peters, who is the unit chief of our research unit. Heather Subert, who is my section chief, but was my unit chief during the process of building this test. And Mike Smith, who's a statistician in our lab, who helped crunch the numbers along with the Ames Laboratory. And with that, I hope to have a plethora of questions that I can answer for you. Thank you.
Well, thank you very much, Eric, and what a great way to start off our final day of the forum. As a reminder, if you have any questions, please type them into the chat. And Eric, anytime you speak, there's always a plethora of questions, so we're going to get right into it today.
All right, John, thank you.
So for the first one, there was some discussion in the chat regarding the difference between a black box and a white box study. Could you just give us an explanation?
Yeah, I'll try to summarize, just simplify it. A black box is you just have a question and you propose that question. You're not looking at the methodology or the processes that go into that. You just want to look at the outcome. So in this situation, we're looking at source conclusions. We have a pool of examiners. We ask them to look at it, and then we look at the results. A white box really is looking at one aspect. So for example, if we wanted to look at the effects of a different type of instruments, does a certain comparison scope affect the reliability or accuracy of the decision? Then we're kind of honing in on a certain aspect of that examination within that black box. We're actually casting light on a particular aspect. So I think that kind of delineates the difference between them.
Great. Next question. By extracting examiners from their quality assurance and verification procedures, would you anticipate the associated error rates of conclusions to be higher compared to those that went through the QA process? In other words, by designing the study this way, are you potentially overestimating the error rates?
Well, intuitively, yes, that's what we're trying to do. If I'm just myself specifically, if I'm the examiner and I'm isolated, I'm outside the quality assurance system, and I'm just making my decision based on all the training and experience that I have, it's just focused on my independent decision. But actually, in one of the slides, I pointed out that we didn't have any, we only had one reproduced false positive. So the idea is that a second examiner isn't going to make the same mistake if I made it. So in the verification of the quality system, if you have a second examiner now look at it, it's unlikely that that second examiner is going to repeat that same mistake.
Excellent. And you mentioned that your laboratory does not eliminate on a difference in individual characteristics. Is that common practice? And second part of this question is, can you describe your identification and elimination process in a little bit more detail?
Sure. I don't know the breakdown of the number of laboratories that do and do not eliminate based on a difference in microscopic marks. There are other labs that do not eliminate on a difference in microscopic marks. The best thing that I can do for you to have an understanding of our methodology, we have an acronym. Always have to have an acronym. So it's we call it E3CV, and it stands for evaluation, classification, comparison, conclusion, and then verification. If you think of ACV, like the latent print examiners, it's very similar. So for any submission, the very first thing that we do at our lab, you open the box and you evaluate, what is it that I have? Is it truly something that my discipline would examine? And if so, then it goes forward. And the very first thing is we look at the item and then we look at the class characteristics. And for this example, we'll pretend that they're bullets. If they're both the same caliber, then they're going to move on to the second stage where I'm going to compare them. But if there are different class characteristics, one's being 9mm, one being 45, they're going to eliminate. So the very first decision is objective measurements, an objective decision where the elimination occurs. Then when we go on to the comparison, now I'm going to look at the two bullets under a comparison microscope. And now I'm moving away from the class characteristics and I'm looking at the individual characteristics that have been imparted on those bullets by the barrel. And now I'm going to compare them. I'm going to look for patterns of similarity between the known specimen, in this case, and a question item. And when I'm doing this comparison, I'm looking for patterns that have sufficient agreement. Sufficient agreement being the type of agreement that I would expect to see from two bullets fired from the same gun, but the agreement has to exceed what I would expect from what would be called a best known non-match, or your worst case scenario. If I do have sufficient agreement, then I can conclude that they were fired from the same gun. And in our laboratory, there has to be a second examiner to verify that decision. And we also have a mechanism to blind verify in some cases, so that the examiner that's doing the verification does not know the original decision from the first examiner.
Great. And then a follow-on question to that. Did you ask the participants to follow their lab's policies on when to eliminate, or did you ask them to report their policy to the researchers so that the researchers knew what the individual lab's policies were?
When we were looking for participants, we were looking for participants that were from accredited laboratories. That was one of the principles, but we were not asking them necessarily to follow their protocol within their laboratory. We were more focused on their utilization of the conditions within the AFTI criteria for making a decision. So that was one of the things that we were asking them to look at.
Great. And you may have mentioned this, but is this study already published or is it still in the process?
It's still in the process.
Okay. Looking forward to that. What is the total number of examiners that made up the 112 errors that were reported?
Now, so I saw that question, and the problem is I don't have all the breakdown, the numbers basically. But what I can tell you is that the errors originated from a small pool of examiners. They weren't cast across the whole community of examiners that took the test. Almost similar to the Baldwin study, the errors were relatively coming from one small population of examiners within the test set.
And your colleague Gene Peters may have answered some of this in the chat, but could you address if you let the examiners who made errors know that they in fact did make those errors?
we did not.
And how many regions of interest did the participants use for their decisions?
Right, so now you're talking about what would be a white box study. Okay, so that's actually a good question. Now you're kind of drifting into what was the thought process in the decision making. So if we wanted to look at, like if we had a way to record, if we asked the participants to record specifically which aspect of this toolmark or toolmarks did you look at to make your decision? Now you're honing into white box type of questions where you're trying to isolate the actual decision point.
Another good question. The elephant in the room is the inconclusive results. What is the plan to address these for sufficiency and/or accuracy? Meaning, how do we parse out correct inconclusive responses and incorrect ones?
It's interesting that it's considered to be the elephant in the room. Because with all sciences, it doesn't matter if it uses more objective measures or it's more subjective, there's always some inconclusive. But with all sciences, you're going to have data that doesn't give you enough information to affect a decision. So in this situation, looking at the results, we were asking the examiners to look at these specimens just like they would have from their training. And they're evaluating them just like they would in casework. So this is a really good reflection of how these examiners are performing when they're looking at evidence. And I think one of the, it's kind of someone that doesn't have, subject matter expertise in the discipline. They're kind of looking at it from the outside, and they don't understand the effects of reproduction of the toolmark and the ambiguity of the information. They don't understand the relevance of the inconclusive. The example that I gave with the false positive is a good example where there was limited information even between the nodes. And so when an examiner is confronted with a ambiguity in the information or not enough information, then you're asking them to basically make a guess on their decision. And that's not a healthy way to handle that type of decision. They basically don't have enough information to make a source conclusion or possibly make a source elimination.
Okay, an audience member made a comment and they said they found it interesting that for paired agreement, you characterize 60% for identified bullets or cartridge cases as very good. How does this compare if we look at easy identifications?
Okay, so that's a good question. I don't characterize any type of identification or actually comparison, put it that way, as being easy or hard. What it really comes down to is the examiner. Some people might look at a pattern and they see, or an exemplar is given where there's a lot of paired agreement. You see a lot of striations between the two and they all match right up. They fall in perfectly. Well, for someone that has expertise in dealing with these types of comparisons, they've been working at it for quite a bit of time and they know where to go and they know how to manipulate the specimens. Actually, let me back up for a second because it's really hard for someone that doesn't actually do the discipline to understand all the intricacies of actually putting the specimens onto the scope and highlighting the toolmark to be able to compare them. So that's a limitation in itself. Can I get them in the right position so that I can see the toolmark and the congruency between the two toolmarks? For the test, our test, we tried to bias it hard. There's no doubt about that. So we got samples that had information that was very limited. And we also set it up so that there were very few known matches, basically a 30-70 split. So, I characterized 60% as being fairly good. I thought that was very good because there was limited information on a lot of the samples for the examiners to extrapolate a decision out of them. So I think for viewers that are listening in and they haven't being able to look at a lot of different sets or had the opportunity to actually operate or basically follow in the footsteps of an examiner, it's hard to kind of understand how they are able to deal with different samples. I don't necessarily coin them as one being necessarily easy or hard. It's the ability of the examiner to move through the information effectively and quickly based on their experience.
Did you find that errors were more prevalent with a certain pistol?
That's a good question. We could tease that out. I don't know the answer to that, but we certainly can. One of the future papers will look at, I talked about it early on in the study, but we were tracking them in lots. So we have two brands, one a lower quality and one a higher quality production model. And we can track the wear and the effects of the examiner's decision over time based on the number of shots that were fired, and those effects based on a better quality production versus a lower quality. But we could answer that question, but I don't have that answer for you right now.
Okay. Could you tell us what the reproducibility looks like if the range of inconclusive results gets lumped into a single generic inconclusive result?
Again, we could tabulate that, but that's not something we parcel it out based on the number of answers that we wanted the examiners to look at based on the AFTI criteria for identification. So you're basically, the question is, could you pool the inconclusives to understand what the error rate would be?
Excellent. Well, Erich, we knew when you accepted to be a presenter that not only would the presentation be outstanding, but we'd have a host of questions for you, both of which did not disappoint us. Thank you so much for your time. And that is all the time we have for questions for today, though.
Thank you very much.